Hello and welcome to another video. Today we'll be learning about polynomial functions and complex zeros. Before we get started, let's take a look at the definition for a zero in a polynomial function. So it says given a polynomial function p of x, if p of a is equal to 0, then a is a 0 or root for p of x. So don't forget that your zeros are always going to come in the form x comma 0, where x is the x value where the 0, root, x-intercept, or solution happens. And then at the bottom says if a is a real number, then x equals a is a 0 of function p, and then x minus a is going to be a linear factor of p. We are used to seeing linear factors. We probably just didn't call them linear factors, but for example, if I have x squared minus 4 equals 0, then that can be factored out into two linear factors, x minus 2 and x plus 2. Again, set it equals 0, and then you use to solve them and say x equals positive 2 and x equals negative 2 are my zeros. So this is kind of what we're talking about today. Like I said, you have seen it before, so it's just going to be a little bit different, kind of elevating it to the next level. You can have repeated zeros or multiplicity. So if you have a linear factor that repeats more than one time or n times, then you can say that the root x0, x-intercept that comes from that linear factor has a multiplicity of n. So typically, we know that the graph of a polynomial passes through the zeros of the graph. So we usually think of that crossing. However, we're going to look at zeros that have a multiplicity greater than 1, and then the graph will behave differently when you have that situation. So here we have our first example. It says the function y equals negative 0.01 times x plus 4 times x plus 1 cubed times x minus 3 squared is graphed on the right side, and then notice the behavior around the zeros of the function. So I am going to zoom in into the function and kind of talk about the multiplicity and kind of how it differs between the different multiplicities for each of the zeros. So at x equals negative 4, I have a multiplicity of 1. So every time you have a multiplicity of 1, you will see that all it does is cross the x-axis, or it goes through. The next 0 is going to be at x equals negative 1, multiplicity of 3. I will go back to the equation and kind of explain that. But every time you have a multiplicity of 3, you will have a graph that crosses through the 0, and then you also can see the concavity change. So I'm going to highlight this in purple, and then I'm going to highlight this in green. So the purple is going to be concave up, the green part of the graph is going to be concave down, and then you can see how at the point where it actually changes, also known as your point of inflection, is going to be that 0. The last one is going to be at x equals 3 with a multiplicity of 2. So every single time you have a multiplicity of 2, you're not actually going to cross the x-axis, you're just going to kind of touch it or bounce off of it. How are you going to remember all this information? The way that I like to remember is think about my parent functions. So if I remember y equals x, again, I only have x equals 0 as my answer. One multiplicity, you can see it crossing, nothing else is happening. For the second one, y equals x cubed. So I have a function that looks like this, but then this one has a multiplicity of 3. Again, you can rewrite it as x times x times x, or you can get x equals 0 3 different times. Again, parent function, you can see it crossing and changing concavity right at the 0. For the last one, y equals x squared. Again, x equals 0, x equals 0. You have two of them, multiplicity of 2. And it's always going to look like that. Bouncing off the x-axis or touching the x-axis, never crossing. So that's how I like to remember it. I feel like that's easy since you should be familiar with your parent functions from Algebra 1 and Algebra 2. You can do the same thing algebraically. So the multiplicity of the 0 is going to be the degree of its factor. So we're basically going to be looking at the exponents to figure out the multiplicity for each of the zeros. So whatever the degree of the linear factor is, that will be the multiplicity, as you can see here. So for this one, for x plus 4, I get my answer to be x minus 4. Since it only happens one time, or I have a degree of 1, then you are going to have a multiplicity of 1. If it's multiplicity of 1, you don't have to specify. If you don't give a multiplicity, then it's implied that it's 1. If it's other than 1, that's when you will see it listed. For the next one, I have x plus 1 to the power of 3. So when I solve x plus 1 equals 0, subtract 1 from both sides, I get x equals -1, which is what this is talking about. And then again, I look at the exponent or the degree, which is 3. So that's why I have a multiplicity of 3. Same thing for the last one, x minus 3 equals 0. Add 3 to both sides, I get x equals 3. That's my actual answer. But since I have a degree of 2 or exponent of 2, that's where the multiplicity of 2 comes from. And then I already talked about this and kind of making a connection between the multiplicity algebraically and the multiplicity graphically and kind of how it works. So let's look at example number 1. It says for each of the following polynomials, determine the degree of the polynomial, find all real zeros, and state the multiplicity for each zero. So I'm going to zoom in here, and then I'm going to find each of the zeros. I do like to put parentheses on it, and then before I get started, I like to ask myself how many of the parentheses have x's inside of them, or how many of them will give me zeros. Well, I'll have 1, 2, 3. So I'll have 3 distinct zeros, or 3 different zeros to work with, and then I can use the exponents to figure out the multiplicity. For the first one, I can do -2 times x cubed equals 0, divide both sides by -2, so I get x equals 0, or x cubed equals 0, take the cube root of both sides. I do get x equals 0 as my first one. Again, looking at the degree of my power, I have a degree of 3, so I'm going to say x equals 0 with multiplicity of 3. For the second one, I have x plus 1 equals 0. Subtract 1 from both sides, I get x equals -1. Again, I have a degree of 1, so I can write multiplicity of 1. If you don't want to write it, you don't have to, because like I said, it's already implied that it's 1. After that, I'm going to continue with the next part. So I'm going to say x minus 4 equals 0. Add 4 to both sides, so I get x equals 4. And then again, I use my degree for my multiplicity. Since my degree is 2, then I'm going to say that I have a multiplicity of 2. And then I will continue on. Oh, and then I need to look at my degree. So to find the degree, all you have to do is add up the multiplicities, and then that will give you your degree. So I have a multiplicity of 3, multiplicity of 1, and multiplicity of 2. So 3 plus 1 plus 2, which will give me 6. And then that's it for example 1a. Looking at example 1b, I noticed that this one is not fully factored out. So I see the difference of 2 perfect squares that needs to be applied before I do anything else. So I'm going to just rewrite the 3. And then these factors are going to be x minus 2 and x plus 2. Again, the order doesn't really matter. And then I have a x minus 2 to the power of 4. Before I continue, I notice that x minus 2 is listed twice, so I can combine those 2 linear pairs as one single one. So I'm just going to put 3, and then x minus 2, I had 4 from here, and then I'm adding 1 more from here, so that will give me x minus 2 to the power of 5. And then I have another x plus 2 over here, and now I have all my linear pairs listed. And I combined one of them because there was 2 of them. So now I can start solving. I'm just going to do this in my head. X equals 2. The degree will be 5, so that will be my multiplicity. I'm going to repeat the same steps for that last one. X plus 2 equals 0, so x equals -2. Again, multiplicity of 1, since that's my degree. Imaginary 1, so every time you have the linear pair just listed one time, it will be multiplicity of 1. Again, you don't have to list it. Looking at C, you can see that it's going to be a little bit more factoring. So for this part, I can factor the greatest common factor between all the terms, which is going to be an x. After that, I'm left with an x squared minus x minus 6 on the inside. And then for this one, you can do the x method if you want. But again, all you're looking for are two numbers that multiply will give me positive 12, but added will give me negative 7. So they both either need to be positive or they both need to be negative. In this case, they're both negative because that's the only one that will give me a negative here. After I do that, I can factor this out further. So same thing, I'm looking for two numbers that multiply will give me negative 6, but add up to negative 1. So x minus 3 and x plus 2 will be my factors. And then I'm just going to rewrite the ones on the right side, x minus 3, x minus 4. I notice that this one is listed twice, so I can do the same thing as before. Keep the x outside by itself. And then I'm going to write x minus 3. I have one here and one here, so that will give me a power of 2. And then I have x plus 2, and then I have x minus 4. Double check real quickly, make sure you didn't miss anything. And we're good. We can do the same thing as before, add a extra parentheses on the first one. Ask yourself how many of these parentheses have x's on them. Well, all 4 of them have x's, so I can need to solve 4 different times. So first one is easy, x equals 0. This one is the one that most people forget, so keep that in mind as you solve your problem. If you have an x outside by itself, you do need to list it as one of your zeros. For the next one, again, I'm doing x minus 3 equals 0. Add 3 to both sides, and then I'm going to get x equals 3. Again, my degree is 2, or my exponent, so multiplicity of 2. X1, x equals negative 1, multiplicity of 1 if you want to write it, and then x equals 4, multiplicity of 1. Again, if it's multiplicity of 1, it's already implied that it's 1, so you don't have to continue putting all of the multiplicities of 1s, but you do have to include it if it's not 1. Okay, let's look at the next page. This part is going to be talking about complex roots. So some polynomials will have roots that contain an imaginary number. So this means that you will not see them in the graph. This is an example of the graph f of x equals x squared plus 1. You can see it on the right side. And then it says to find the zeros of f of x, you would set the equation x squared plus 1 equals 0. Well, when you try to solve this equation, subtract 1 from both sides, you get x squared equals negative 1. If you try to take the square root of a negative number in the real number system, you will get undefined. So if you try to put that on the calculator, but you do have to memorize that the square root of negative 1 is plus or minus I. And then again, you will not see them on the graph. If you look at this graph, you will never touch or cross the x-axis, but you do have this imaginary or complex roots that is still part of your answer. Some important things about imaginary roots is that they always come in pairs, no matter what. And they will look similar to each other. So think of it like buying a pair of shoes. They have the same design, but physically they are a little bit different than the other one. So if this one is a plus bi, the other one called the conjugate pair will be a minus bi. So the a part or the real part will always be the same, and then the imaginary part or the part with the I will have the opposite sign. So in this one I have a plus, the other one is a minus. So I'm just going to move that over there really quickly. And that's going to be the conjugate pair. So let's look at example 2. They want you to find the conjugate pairs for each of the following complex numbers. So for a, you're doing 4i. So again, it's just going to be negative 4i, since that's only this part of the equation, the right side. For b, we're going to do the same thing. So instead of it being negative I, the conjugate will be positive I. And then for c and d, you can see that they're already using both parts, the left and the right. So for c, it's going to be 2. That part is your a, which will stay the same. And then the imaginary will have the opposite sign. So final answer will be 2 plus 3i. Same thing for D, the -4 will stay the same, and then the part with the I, change the sign to a negative since it's already positive. Okay, let's look at the fundamental theorem of algebra. It says a polynomial of degree n has exactly n complex zeros when counting multiplicities. I like to simplify this and just say my degree is going to be equal to my real roots plus my imaginary roots. You'll see me using this equation throughout the problems, but that's all it means. Take the number of real solutions, take the number of imaginary solutions, add them together, and that will give you your degree. Keep in mind, imaginary always come in pairs. If you have one, it's implied that you have to conjugate. That is also a root of the function that you're working with. So example 3 says the graph of the polynomial function f of x is shown in the figure above. It is known that x equals I times the square root of 3 is a 0 of f. If f has a degree of n, what is the least possible value of n? So what I'm going to do is I'm going to make some notes in my graph and say x equals -1. Again, I can see it bouncing off or just touching the x-axis. So I know this one will have a multiplicity of 2. Then I look at x equals 3. I see it crossing the x-axis, not changing concavity. So that one will just be a multiplicity of 1. So looking at my equation, for my real roots, I can see a multiplicity of 2 and a multiplicity of 1. So that will be 3 real. Plus, and now we can focus on the imaginary part. So again, they told me already that I have this imaginary root at x equals I times the square root of 3. So I know that the conjugate for it will be negative I times the square root of 3. That's all the information that I have. So I know I have 2 imaginary roots. And then I'm going to say that the least possible value is going to be 5. So I'm going to say n has to be greater than or equal to 5. And then I'm going to make in parentheses n has to be an odd number. We'll talk later on why it has to be an odd number, but very quickly, this is going to be an odd degreed function because if you see the endpoints are opposing, they're pointing at opposite sides. If it was an even function, they will both be pointing at the same direction, which we will talk about a little bit more in 1.6. We can also solve polynomial inequalities using a graph. So when we write f of x, don't forget we're referring to the y values on the graph. And then if we say f of x is greater than 0, that means that the graph of f of x is above the x-axis. If we say f of x is less than 0, meaning the graph is below the x-axis. So the x-axis will separate what's greater than 0 and what's less than 0. So if it's greater than 0, we're looking at the positives. If it's less than 0, then we're looking at the negatives. Keep in mind you might also have less than or equal to or greater than or equal to, and then that will be similar, but now you're including the endpoints because of the equal symbols. So let's look at the questions and see what they're asking for. So the first thing I'm going to do is I'm going to highlight the x-axis on red because that's going to determine my separation for my values. So for question A says where do those f of x equal 0? So again, if you remember, they're basically asking for the x-intercepts. Root 0 solution. So I have 3 of them. First one is going to be at x equals -3. The next one is going to be at x equals -1. And then the last one at x equals 3. For B, they want to know where I'm above the x-axis or greater than 0. So I'm going to highlight this in green. Hopefully you can see that. Again, endpoints should not be included because it's just greater than. And then I'm going to write my intervals. So starting at x equals -3 to x equals -1, your y values are greater than 0 or positive. And then from 3 all the way to infinity, they're also positive. Looking at C, they want to know where your f of x is less than or equal to 0. So on this one, I do have to include the endpoints. I'm just going to highlight them here. So I want to be at the red line or below the red line. So I have two different intervals. The first one from -infinity to -3. Again, it has to be included. And then from -1, and then I stop being negative at x equals 3. So now let's move on and kind of use this information to solve nonlinear inequalities or polynomials. So we're going to have 4 different steps. Step number 1 says to solve for f of x equals 0. I am going to add on here, move everything to the same side and factor if necessary. So this is going to be kind of added extra steps. That is part of step number 1. You don't always have to do it, but when you do, it's very helpful to have it in your notes. After you do that and you solve it, you're going to use the numbers that you get from there to create a sign chart. So a sign chart might look something like that, and then depending on the numbers, they will go here. And then these numbers will represent your x-intercepts, zeros, roots, or solution. After that, you're going to test the values to see if the values in the interval are positive or negative, depending on the situation, again. And then after that, you're going to interpret the sign chart and then the inequality that they gave you to figure out if you're looking for the positive y values, negative, or negative y values. Be sure to write your answer in interval notation and then think about the endpoints. So the endpoints you're asking yourself, is it included? So I need to use a bracket, or if it's excluded, where I need to do a parentheses. Okay, so let's look at example number 4. I don't have to move anything because everything is on the same side. And I don't have to factor because it's been factored out. So now I can start solving for my zeros. So x equals 3, x equals -1, and x equals -4. So again, I have 3 unique zeros. So when I draw my number line, I will have 4 different intervals to work with, because you always have one more interval than the number of zeros. After that, I'm going to put them in order. So -4 is going to be the smallest, then -1, and then +3. So for this one, I'm going to show you all the steps that you need to do, and then after that, I'll kind of start using shortcuts to do it once we know where the numbers are coming from. So for this first interval, I need to pick a number less than -4. So I'm just going to pick -5. After that, you're going to plug them into this parentheses and figure out what the sign would be. So basically, this whole interval will have the same sign. So if I get a plus, that means all the numbers from -infinity to -4 are positive. And if I get a negative, all the numbers from -infinity to -4 are negative. So for this one, I'm going to write all the steps. So -5 minus 3, -5 plus 1, and then -5 plus 4. So again, all I care about are the signs. So if I take -5 and take 3 away from it, I'm still negative. If I have -5 and add 1, I'm still negative. And then if I have -5 and add 4, I'm still negative. So here, a negative times a negative will give me 2 positives. And then a positive times a negative will give me a negative. So now I know that from -infinity all the way to -4, my y values will always be negative or below the x-axis. For the next part, I am going to pick a number between -4 and -1. So I'm just going to pick -3, and then I'm going to plug that number into this parentheses. So -3 minus 3, which is negative, or -6, -3 plus 1, which is -2 or negative, And then for the next one, negative 3 plus 4, which is going to be positive. A negative times a negative will give me a positive. This interval, if you have a negative and a positive, you always want to pick 0 just because it's easier to work with. You don't have to think a lot. 0 minus 3 is negative. 0 plus 1 is positive. And 0 plus 4 is positive. So I know that this whole interval is going to be negative. Last one, number bigger than 3, like 4. 4 minus 3 is positive. 4 plus 1 is positive. And then 4 plus 4 is positive. So since they're all positive, my last interval is positive. There is a shortcut since we already learned about multiplicities. As you can see, all of these root zeros, x-intercept solutions have a multiplicity of 1. So once I find the first one, I know that it's always going to cross over into the other one. So if I'm in the negatives and I cross, then I will move into the positives. If I'm in the positives and I cross, I'm going to be into the negatives. If I'm in the negatives and I cross, I'm going to be into the positives. If you're not comfortable using multiplicities, just use the sign chart and plug everything in. It's not that much work, and you probably will get the correct answer, which will make it so much better. Let's look at example number 5. Again, I don't have to move anything to the other side because it's already been moved, and I don't have to factor. So I can start solving x equals negative 2 and x equals positive 5. Draw my number line. Now I only have 2 different numbers, which means I'm going to have 3 different intervals. So I'm going to pick a number less than negative 2. Keep in mind that now you're squaring. So when you do your sign chart, you do have to square. So negative 3 I'm going to pick. Negative 3 plus 2 is going to give me a negative. And then I have to square it. And then negative 3 minus 5 will also give me a negative. Well, when I do this, a negative squared will give me a positive times a negative, which will give me a negative as my final answer. Remember what I said. If 0 is in the interval, pick 0 to make it easier. So I'm going to pick 0. 0 plus 2 is positive. And then I'm going to square it. And then 0 plus 5 is negative. Well, positive squared is still going to be positive times a negative, which will give me a negative. And then for the last one, a number bigger than 5, like 6. 6 plus 2 is going to be a positive, and then squared. And then 6 minus 5 is still a positive. So a positive times a positive will give me a positive. If you want to use multiplicities, don't forget this one has a multiplicity of 2, meaning it will not cross the x-axis. It will bounce off, so this one bounces off from the negatives, bounces off of the x-axis and goes back to the negatives. This one has a multiplicity of 1, so it will cross and change from negative into positive. After that, I'm looking at the inequality less than or equal to 0, so I only care about my negatives. So that's what I'm going to look at. Negative infinity all the way to positive 5, and then I can close my interval. I just realized that I never finished example number 4. So for example number 4, I want greater than 0. So I'm looking at the positives. So from negative 4, or x equals negative 4 to negative 1, and from 3 to infinity is when I'm positive or greater than 0. Sorry about that. Got excited, thought I was done. Okay, so now we can determine the degree of a polynomial given a table of values. So if they give you a table of values with equal width input intervals, we can determine the degree of a polynomial by examining successive differences in the output values. The number of successive differences needed for the differences to be constant is equal to the degree of the polynomial. Well, the equal with input intervals is talking about the x values. So for your x values, you do have to be moving by the same rate or the same number. So from 1 to get to 3, I do need to add 2. From 3 to get to 5, I need to add 2. From 5 to 7, 2. 7 to 9 plus 2. If you don't have that, you cannot use this method to solve the problem. And then I'm going to do the same thing with the y values and do it as many times as needed until I get that constant that I need. So to go from -2 to -3, I need to subtract 1. From -3 to -1, I need to add 2. From -1 to 4, I need to add 5. And then from 4 to 12, I need to add 8. Uh, since I don't have the constant, I'm gonna keep on going until I do get that constant. From -1 to 2, I need to add 3. From 2 to 5, I need to add 3. And then from 5 to 8, I need to add 3. So this is the constant that I was talking about. How many times did I do it? Well, I did it twice. So I'm going to say the degree of my polynomial of polynomial f of x is 2 because the second common difference is constant. And that's all I need to do for that one. I am going to do the same thing for b and see if I have equal length input intervals. So from 0 to 3 is 3, from 3 to 6 is 3, from 6 to 9 is 3, and from 9 to 12 is 3. So now let's go to the right side. From -2 to 0, I'm adding 2. From 0 to 10, I'm adding 10. From 10 to 17, I'm sorry, from 10 to 27, I'm adding 17. And then from 27 to 50, I'm adding 23. Again, looking for the constant. I don't have it yet. So I'm going to do this one more time. From 2 to 10, I add 8. From 10 to 17, I add 7. And then from 17 to 23, I add 6. Still not constant. Keep going until you find that constant. From 8 to 7, -1. From 7 to 6, -1. So since I have 3 different lines, or I did the difference 3 different times, I am going to say the degree of g of x is 3 because the third common difference is constant. So please make sure that this number and this number matches. So the first one was the second common difference, so that's why the degree is 2. And then on this one was the third common difference, that's why the degree is 3. Now let's talk about even and odd functions. In order for you to say that a function is even or odd, it has to fit the specific definition given to you right here. So for an even function is symmetric over the y-axis. Please do not get this confused with even degreed function, because that would just tell you where the endpoints are pointing. So if both endpoints are pointing up or down, then you have an even degreed polynomial. In order for you to have an even function, it has to be symmetric over the y-axis, which you can see here. I'm going to highlight for you. Now, let's look at some of the pattern in the numbers. So if I look at this point right here and this one is going to be -2, -3. And then this one's going to be +2, -3. Notice how the x's have the opposite signs, and then your y values are exactly the same. If we look at other points, it'll be the same thing. So 3, 2, and this one will be -3, 2. It will happen throughout the whole graph for a even function. When we look at odd function, then you have to be symmetric about the origin. That is your definition. So for this one, you can imagine that you're folding it along the y-axis. Every single number overlaps. This one is going to be a little bit differently, because for this one, you have to do 2 reflections in order for you to be symmetric over the origin. So I'm going to take this part, and then I can apply the reflection over the x and the y-axis on the same graph, and then it will overlap with the other one. So if I take this one, and then I reflect it over the y-axis first, it will look something like that. And then if I take that highlighted red part that I just drew and reflect it over the x-axis, it will overlap completely on top of the other part of the graph. It doesn't matter where you start. So let's do it the opposite now. I'm going to start on the right side, and then I'm going to reflect over the x-axis first. So that will be the highlighted red part. And then if I reflect over the y-axis, then that comes and overlaps on this side. If we look at the points, we also notice that there is some pattern here. So for this one, it's going to be 2, -2. And then for this one, it's going to be -2, 2. So you can already see how they have opposite signs for both the x and the y, which is different because on this one, the y's were exactly the same, and then only the x's had the opposite sign. You can look at other numbers. So this one is going to be -3, 0. And then this one should be +3, 0. And keep that in mind because you can use that with tables, or you can use that with other functions that you can draw and add more points based on what was given to you. You do have to memorize this equation because if they give you an equation, you should be able to figure out if the equation is odd and even based on the equation that was given to you. So if we look at example number 7, we can figure out if this is an even function, odd function, or neither. I do like to check for odd first. So if you remember the equation from the last page, it's going to be f of -x equals -f of x. So basically, this left side we're evaluating -x, or we're replacing every single x in my equation with -x. The one on the right, I'm distributing the negative to every single part of the equation. So I'm going to do it. So 2 times -x to the 4th minus -x squared plus 5. And then I'm trying to see if that's equal to -2x to the 4th minus x squared plus 5. And again, this is to check if my function is odd. After that, I'm going to simplify. Don't forget, if you have a -x to the 4th power, all it means is I multiply -x times -x times -x times -x. After that, I know that these two multiply will give me +x squared, and then I know that these two multiply will give me +x squared. So this actually simplifies to +x to the 4th. Don't forget you have a 2 in the front, so this will give me 2x to the 4th. And then the same thing happens here. -x times -x will give me +x squared, but I have a negative in front. So -x squared, and then the 5 didn't get affected at all, so I'm just going to rewrite it as +5. After that, I'm going to distribute this negative to every single part of my equation on the right side. So -2x to the 4th plus x squared minus 5. After that, I'm going to compare these two equations. If the equations are exactly the same for every single sign, then I know that it's an odd function because that's what I'm checking for. When I look here, I know that these signs are all opposites of each other. So I know that this is not an odd function. So to check for even is really easy because the equation to check if something is even is f of -x equals f of x. Well, I already did the f of -x when I checked for odd. So all I'm going to do is I'm going to recycle my work and write it down on the left side. So 2x to the 4th minus x squared plus 5. And see if it's equal to my original. So I'm going to go up here and grab my original and copy it. 2x to the 4th minus x squared plus 5. Again, I'm going to check to see if these two equations are exactly the same. If they are the same, then I know that my function is even. So when I look here, I notice that they are exactly the same. So I'm going to make a note that this is an even function. The next example, you're doing the same thing. So again, I'm going to check if it's odd first. And then if you remember that equation, it's going to be f of -x equals -f of x. So I'm going to take my equation and replace all my x's with -x, simplify, and then see if it's equal to the other side. So -x cubed plus 3 times -x minus 1 equals -x cubed plus 3x minus 1. On the left side, when I simplify negative x cubed, the negative does stay because it's an odd number. And then 3 times negative x will give me negative x, and then the minus 1, just bring it down. I'm going to distribute this negative to all three numbers, so negative x cubed minus 3x plus 1. I notice that they are not the same, so I'm going to say it's not odd, and then I can check for even. So again, f of negative x equals f of x, or my original function. I know I'm using f, you can use k if you want, but it's just easier for me. So again, I'm going to recycle this work, negative x cubed minus x minus 1, and see if it's equal to my original x cubed plus 3x minus 1. I notice that they are not the same, so it's also not even. So I'm going to say that my function is neither. Looking at C, you can do it two different ways. You can do it using the reflection. So I'm going to take this side, reflect it over the y-axis first. So it will look something like that. Reflects over the x-axis again. So this side at the top will overlap with the bottom. Or you can look at some points. So this one is going to be -1, +3. And then this one is going to be -3, -1. Same thing here, 2, 0, -2, 0. Again, you can see that the signs are all swapped or opposites of each other. So that will tell me that this is an odd function. And then for this one, again, if I try to do the reflection at the origin, it will not work. Because again, if I take this half and I reflect it, it will look like that. If I reflect over the x-axis, it will not look like the other side. It will not overlap. So if I try to look at the to see if it's even or not, again, I want to be symmetric about the y-axis. You are symmetric over this random x equals +1. But again, in order for you to be an even function, it has to be symmetrical about the y-axis, which is not. So since it failed the odd test, it's not odd. You failed the even test, it's not even. So I'm going to say that this one is neither. Well, thank you for watching this video. Hopefully you learned something today. Have a great day. See you next time.